All right, welcome back. Welcome back. All right, so we've got joint probability distributions. We have marginal probability distributions, and now we have another one in definition 311 in our e-text. Let x and y be two random variables. Two random variables. The conditional distribution. Conditional distribution of y given capital X takes on some value, little x, is notated as follows. This is f, space here, f of y given x, just like the conditional probability. All right. And this, how does one compute this? Think about the relationship that you had with conditional probabilities of events, right? It was the probability of the intersection divided by the probability of the given. Well, we're going to take the analog there in terms of our distributions here. This would be the joint distribution, which mirrors the intersecting probability, divided by the marginal distribution of x, which mirrors the probability of the given event. Obviously, as we have before with conditional probabilities, that the ordering on conditioning matters. So I would say similarly, the conditional distribution of x given y, conditional distribution of x given capital Y will be f of x given y. And that is the same joint distribution, but now we divide by the marginal of y. There we go. Okay, so we have that. Conditional distributions, the conditional distributions, all right? Let me go ahead and try to continue that example we had recently about selecting pens. Continued from selecting two pens. Let's see if I can't pull down that table that we already made. We spent so much time on making earlier right there. So let's see here. Can I get that somehow? I go... Can start copying down these numbers in your notes if you want this. Is this the copy button? Is that what that means? Copy. Okay. And keep scrolling. Where's my paste button? Aha! Perfect. Get this out of here. There we go. So we had that. Looks good. Let's just put our y back right there. All right. So we have that so far. Okay. So there's our distribution. Let's go ahead and find the probability that x is equal to 0 given y is equal to 1. The probability that x is equal to 0 given that y is equal to 1. Okay, well, let's go ahead and take a look at this. There are a couple ways that we can go about this. The first way that I'm just going to go about it in a way that lets us work through all the mechanics. All right, so we want the probability that x is equal to 0 given y is equal to 1. Okay, so one way to do that would be to use the actual distribution, the actual conditional distribution of x given y equals 1, right? So we could start by finding the distribution of x given y is equal to 1. And according to the most recent definition, then, that is the joint distribution of f of x comma y. But notice, in these things, these conditional distributions, you're given specific values. So we should substitute those in where we can. Divided by the marginal distribution of y when y is equal to 1. Right? Take a look at this. This is f of x comma y divided by h of y, except here we're given y is equal to 1. So we have that. Okay? What do we have here? What is h of 1 going to equal? H of 1 is the marginal distribution of y evaluated at 1, and we know h of 1 is equal to 12 over 28. This is h of 1 right here, right? We sum that up, and so this is equal to, what is this equal to? 12 over 28 is also 3/7 if you reduce that down, right? Divided by 4 would be 3/7. Okay, so f of x given y equals 1 is the joint distribution divided by 3/7, or equivalently multiplied by 7/3. So the conditional distribution is 7/3 times f of x comma 1. F of x comma 1, right? And in fact, this is a distribution, and so we can say that this is good for x equaling 0, 1, or 2. That is our joint distribution right there. That's your joint distribution. Now, we can use this joint distribution. What is the probability that x equals 0 given y equals 1? Well, then we just want to evaluate this, right? We just want to evaluate this. The probability that x equals 0 given y equals 1 then is equal to 7/3 times f of 0 comma 1. And so this is 7/3. What is f of 0 comma 1? You go on your table. When x is 0, y is 1. We see that that is 6/28. 6/28. And what do we have here? 3 goes into 6 twice. 7 goes into 28 4 times. 2 over 4 is a half. That is the probability. 1/2. 1/2. Okay. Now, that's a lot of extra work, in some sense, to just answer this probability question, right? But it is nice because this actually does, what I like about showing all these mechanics is it shows us exactly what the conditional distribution actually is. Which is useful because if you have other probability questions, you can work with this very quickly. You don't have to rederive it every single time. However, if this is the only question, the only probability question you have to answer, alternatively, you could just directly compute that from the table using what we know about conditional probabilities, right? We could just say the probability that x is equal to 0 given y is equal to 1, using the definition of conditional probability, would be the probability that x is equal to 0 and y is equal to 1 divided by the probability that y is equal to 1. And we go ahead and look at the table. X is 0, y equals 1. That's 6/28. What's the probability y is equal to 1? You can add up that row. That y is equal to 1. 6/28 times 6/28. Right? 6/28 times 6/28. Hold on. I need to add these together, not multiply. Add. 6/28 plus 6/28 is 12/28. And 6/28 divided by 12/28, that reduces down to a half. Sure enough. Okay. So there's a discrete. Let's take a look at a continuous example of a conditional distribution. Let's say f of xy is equal to, start a fresh one from scratch. Let's say x times 1 plus 3y squared. Close that parenthesis off, all over 4. This is good when x is between 0 and 2. And y is between 0 and 1. And 0 otherwise. Okay. All right. Let's do a few things here. Remember, in order to find the conditional distribution in the continuous sense, well, in both cases, you have to be able to divide by the marginals. So you have to know what the marginals are. All right? And so in the continuous case, you almost always have to go through the process that we did in blue here, because there's no shortcut like we have in red where I just look these values up in a table, right? So I really do need to know what the marginals are before I do any sort of conditional distribution. So let's go ahead and just work through that and get a bit of extra practice there. Let's find g of x, and we'll do h of y right after this as well, okay? So let's go ahead and work through this real quick. So let's see here. So what is g of x? Remember, g of x would be the integral of our joint density. We want the marginal with respect to x left, so I want to get rid of the y, so I integrate over all the y's. All right. So our integration bounds y, if we look at our joint PDF, y just goes from 0 to 1 here. And then this is x over 4 times 1 plus 3y squared dy. Okay? Remember, in your joint PDF, or in our integration, we're treating x as a constant when we're integrating with respect to y. So x over 4 is just a constant, and so if we want to, we could just factor that constant out in front of the integral. And now we just have a regular old-fashioned single variable integral with respect to y to do. And so let's go ahead and do this. X over 4 times the integral, what's the antiderivative of 1? It's just a y. And the antiderivative of 3y squared should be y cubed. We want to evaluate all of this as y goes from 0 to 1 here. This is equal to x over 4 times, what's the evaluation when y is equal to 1? That's 1 plus 1 cubed minus x over 4 times the evaluation at 0. 0 plus 0 cubed there. So that second quantity zeroes out. And all we're left with is x over 4 times 1 plus 1 is 2. And all of that is just 0. So 2x over 4 or x over 2. So what is g of x then? This means that g of x is equal to x over 2. For what x values? Look at your bounds given in your joint distribution. X goes from 0 to 2 there. X goes from 0 to 2. Okay. Looks good. Looks good. For good measure, let's just go ahead and find the marginal with respect to y as well. So remember, h of y then, same setup. We're going to integrate over all possible values from minus infinity to infinity of our joint density, but with respect to x. And x, if we look at our joint density, right, x goes from 0 to 2. So we integrate x over 4 times 1 plus 3y squared dx. And again, 1 plus, think about this, treating that y as a constant, then 1 plus 3y squared is multiplying a constant. And so you can factor that constant out in front if you want to. Well, it's a little bit overkill, but why not? 1 plus 3y squared. Let's take the divided by 4 with it. So you're integrating from 0 to 2, x dx. X dx. And so let's see what we have here. We have 1 plus 3y squared divided by 4. And then what is the antiderivative here? The antiderivative is x squared over 2, evaluated as x goes from 0 to 2. So x goes from 0 to 2. So what do we have then? 1 plus 3y squared over 4. What happens when you plug in x equals 2? You got 2 squared over 4. Sorry, 2 squared over 2 rather. Minus the evaluation when x is 0. That's 0 squared over 2. So let's see. This is 0. 2 squared. 2 squared is 4. 4 over 2 is 2. So that's, this is just being times 2 then. So this is 1 plus 3y squared over 4 times 2. So then we can cancel that with that, and that will be divided by 2 then. So we have 1 plus 3y squared divided by 2, and this is good for y between what and what here? Go back. Y is between 0 and 1. Y is between 0 and 1 here. Y is between 0 and 1. Okay. Good. So we got both of our marginals here. So now with those marginals, then in the continuous sense, if you want the conditional distribution, let's say f of x given y, if we want to find f of x given y, now we have the marginal ready to go and we use that definition, right? F of x given y, according to that definition, is the joint density divided by the marginal density. And so we can just directly substitute these functions in, right? What is the joint density? The joint density is x over 4 times 1 plus 3y squared. So this is x 1 plus 3y squared over 4. Then this is divided by h of y, and h of y we have as 1 plus 3y squared all over 2. That is our joint or conditional density. And now we just need to clean this up a little bit, right? This multi-story fraction here, dividing by that fraction is the same thing as multiplying by the reciprocal. So let's clean this up. So instead of dividing by 1 plus 3y squared over 2, I'll multiply by the reciprocal times 2 over 1 plus 3y squared. And let's take a look at what we have here. That's going to cancel there and leave me with a 2. 1 plus 3y squareds cancel. And what do we have left then? X over 2. X over 2. So f of x given y is equal to x over 2. F of x given y is a conditional distribution, but it's a conditional distribution for x, right? And so this is going to carry down your x domain as well, which was between 0 and 2. There's the conditional density. All right. And now once you have that, then again, this is just like this is just another distribution for x, right? Like it's almost like the marginal. It's conditional. It's almost like the marginal, but you get to answer any of those questions by doing a single variable integration. So for example, let's say you wanted to find the probability that x is between 1/4 and 1/2 given y equals 1/3. Given y equals 1/3, all right? This is kind of interesting. There is no y in your conditional density, but if you had a y value here, you just plug in 1/3 for y. Y doesn't explicitly show up, so we don't really need that. So how do we answer this? We just need to integrate our conditional density, which is x over 2. Integrate our conditional density. Let's do this in general. Integrate your conditional f of x given y equals 1/3 dx, and you're going to take your x bounds here from a to b, where this is your lower bound a and this is your upper bound b. So this goes from 1/4 to 1/2, right? So we're going to integrate from 1/4 to 1/2. And what is f of x given y? This is just x over 2 then dx. So now we just do the calculus. The antiderivative of x over 2 should be x squared over 4. Now we evaluate this from 1/4 to 1/2. Plug in your endpoints. 1/2 squared over 4 minus 1/4 squared over 4. We run that through a calculator. We should get 3 over 64. 3 over 64, okay? 3 over 64. You might be thinking, well, this is kind of interesting because x over 2, x over 2, this is the conditional distribution. The conditional distribution does not depend on y at all. Well, conditional distributions are used to compute conditional probabilities. So you're telling me that the conditional distribution or a conditional probability of x, y doesn't affect that at all. So does that sound like something? Does that sound like a property? Is there some way we can describe that relationship between the random variables x and y? Well, currently we don't really have ways of talking about relationships between random variables, but this does directly correlate to something that we did used to talk about in terms of events and certain things being independent. Definition 312. Let x and y be two random variables with joint probability distribution, joint distribution f of xy, and marginal distributions. Just defining the notation for the definition here. Marginal distributions, we'll use g of x for the marginal distribution of x and h of y for the marginal distribution of y. Okay, so x and y are statistically independent random variables. Statistically independent. Statistically independent if and only if f of xy, I should be clear, f of xy is equal to, let's be careful, g of x times h of y for all x and y. For all x and y. Okay? And I want us to just look at this and think about the parallel that this is with what we had for independence of just events. Okay? And how do I want to go back here. Let me just, we go back in our notes. Chapter 2. Where's independence? Is that in this section? Let's take a look. Is that in this section here? Where's independence? Definition 211. Two events A and B are independent if and only if the conditional probability. That's true. That's not the one I was looking for here. Looking for a different theorem. Theorem 211. A and B are independent if and only if the probability of A intersect B is the product of the individual probabilities. Probability of A times the probability of B. Look at Theorem 2.11. That parallel with what we have here. The joint PDF, the joint probability, is equal to the product of the individual or the marginal probabilities, right? Look at those parallels, okay? Look at those parallels, all right? Now, in the last example, we had f of x comma y equals x times 1 plus 3y squared over 4, right? We had that. And we had g of x, we found the marginal to be x over 2, and we found h of y to be 1 plus 3y squared over 2, I believe, right? Is that right? What did we find for h of y? H of y is 1 plus 3y squared over 2, and g of x is x over 2. Okay? And just notice x over 2 times 1 plus 3y squared over 2 here is x times 1 plus 3y squared over 4. Over 4, okay? And so that's a good indication, that's a good check, that those are, in fact, x and y. In the last example, x and y were, in fact, independent, okay? X and y were, in fact, independent, all right? There's a little bit more details actually going on behind the scenes. To just do this product right here, g of x times h of y, that's good. It's also important that the bound is a rectangle. So 0 to 2 and 0 to 1, if you draw that in your plane, it's a rectangle. But For the most part, I'm not going to worry about that. That's maybe getting in a little bit of a deeper level. But I do want to mention that this carries over in the discrete case, but it's not nearly as convenient. In the discrete example we had, it's not nearly as convenient because you don't have explicit algebraic functions that you can multiply. You can't just do g of x times h of y in a generic sense. You have to do this for all of your possibilities. So in the discrete example, we had the following marginals from that table, right? We had 0, 1, and 2. We had 5/14. This is the pens example. If you look at your columns total and your row totals from the pen example, we had g of x, and we had h of y, 0, 1, and 2. And this was 15/28. This was 3/7, and this was 1/28, I believe, if I reduce that down. Okay? All right. So in the discrete example, you can't just, there's no quick way to do this. You have to check all of your cases, essentially, right? And so it's more likely, almost, that when you're doing these questions, that you'll find one that doesn't work. Because you only need one, right? This has to work for all x and y. If it doesn't work for one, then they are not independent. All right, so let's just go ahead here. So, for example, what is f of 0, 0 equal to? Well, for that, we got to go to our table. Let me grab a couple entries from the table before we get too far. Let me grab f of 0, 0. Let me grab f of 0, 1 from our table here. Page back to that table. So f of 0, 0 is 3/28, and f of 0, 1 is 6/28. Okay, so that's f of 0, 0. So is this equal to g of 0 times h of 0? Let's check. G of 0 is 5/14. H of 0 is 15/28, right? Looks good. So what do we have here then? This is, so what is this? This is 5. I don't have a calculator on me. 5/14 times 15. Can I get some math help here? Let's make this 14. It's not going to let me fix it. Let's just rewrite that real quick. I don't have a calculator on me, so 14. What is this equal to? Evaluate. 75 over 392. This is not equal to 3/28, right? Not equal to 3/28. So they are not independent, and you can stop there, right? They are not independent. You can stop there. Okay, you don't need to do any more. However, suppose it did work out, okay? Suppose that when I multiply these out, suppose it did end up equaling 3/28, right? Let's just go ahead and do that real quick, right? So let's just say, suppose that g of 0 times h of 0 was 3/28. That does not prove they're independent, okay? Then they might be independent, but you have to check all of the pairs. They might be independent. It's not good enough. You'd have to check all of them, right? And so that's why I grabbed another one, f of 0, 1, and I could check this and say, is g of 0 times h of 1 equal to 6/28, right? And I would do that. Well, what's g of 0? That is 5/14. And what is h of 1 equal to? That is 3/7. So this, 3 times 5 is 15. 7 times 14 is 98. 1598 is not equal to 6/28. Okay? So even if it worked out the first case, if I tried this second case and it didn't work out, this is enough to show they are not independent. X and Y are dependent. Okay? Even if it worked for one, it doesn't matter. It has to work for all of them. So you'd have to go through everything. You have 3 options for X. You have 3 options for Y. You would have 9 pairs to check to prove independence in the discrete case. All right. Good. That will do it for us. That closes up this section of our notes. Good time to start working on some practice problems and trying to attempt some mastery points. Post questions and problems we're having with the online homework in the discussion thread below.